Right, welcome back. Last class we ended off at APL tree deletion, I think. Correct me if I'm wrong. Last recording seemed to have gone kind of corrupted. I'm going to look into it more later, but it's probably never going to be posted. But I'm pretty sure we left off at APL tree deletion. Deletion is, as the slide says, already finicky with BSTs, and it's about to get a bit finickier because of tree rotations, but all the ideas you know and love still apply. The deletion algorithm has 3 cases, just like binary trees. In general, it works just like binary trees, except once you delete a node, and make the necessary replacements to delete that node in a binary tree, you also have to go upwards from a leaf to the root, rebalancing the tree by rotating nodes as needed. So in the first case, we're going to delete key 8. I think this was the easiest case with binary search trees. Before, we would have just deleted that 8 and moved on with our lives. But these are APL trees, and just deleting 8 and moving on would have made the tree unbalanced. Oh. 412, it's interpreting the binary tree nodes as a phone number? No, it wants me to call someone.
Scan the text and it's just here's a number. All those numbers in sequence. I thought it was a phone number.
Yeah, I kind of want to call the binary tree number, but they probably won't like it. Yeah, I know. I said cancel. Whatever. So what I meant to do was start drawing on the screen. The right child's height is minus the left child's height is -2. The definitions that we started this topic with mean that this tree's balance is unacceptable, and we need to rotate the tree along node 6 in order to rebalance it. In general, we start at the place where we deleted the node and then go upwards towards the root. Rebalancing is necessary. So after we're done rebalancing, I won't bother drawing the whole thing out, but 3 is going to replace 6. 6 is going to become a new right child, and then we're going to move 4 over here so that 3 doesn't suddenly have 3 children. It's a binary tree, not a trinary tree. Or a ternary tree? I have no idea. This is what it looks like after. We luckily don't need to get into that nasty double rotation case. The single rotation on that node just works. Here's something fun to do while you're studying. Find a key, so a value in the tree, such that deleting that value from this tree requires more than one node to be rebalanced. And then draw the end result of deleting it. While I was reviewing the slides, this took me a little while to figure it out, so I highly recommending tuning out while I tell you the answer, and then taking some time so you forget the answer, and then attempting this on your own. Once you're able to get it, it'll show a good understanding of APL trees. Turns out 1 is the node that ruins the balancing. So we've got trees of height -1 and 1 on node 3. So we're going to have to rebalance node 3. So we're gonna end up with, I think this will require double rotation. The particulars of the situation aren't that important, but we'll end up with nodes in this sort of arrangement, making that node have children with heights 0 and 0, and thus be balanced. So after we rotate this, we're going to end up with 3 having height 1 after the first rotation. Whereas this guy over here is going to have height 3. This was okay before because 3 started out as having height 2. The heights were off by at most 1, so it was fine. But after rebalancing 3, it has height 1, which is, by our definitions, way, way less than height 3. So we're going to have to pull off a big rotation. If I put a question about this on the quiz, it'll be easier than this. And we'll end up with 15 at the top, 10 on the left. This whole thing moved to the left, and then 20 being the new right. And it'll look something like this. This is a nice example of our more general algorithm of moving up the tree and rebalancing as necessary. After deleting that node 1, node 3 still had height 2, and thus the root node was still balanced. So if we went from the root to a leaf, we wouldn't have noticed the unbalancing that resulted from our first rotation. Starting from the leaf and moving upwards lets us, catch all losses of balance that happen. So since we're moving up the tree from the root, you may remember from earlier classes, we discussed how the height of the tree with n nodes is always big O of log n. And additionally, when we change anything about the tree, it only affects nodes that are in its path to the root. So like deleting 1 upset the balance of node 3 and 10, but didn't change anything about 13 or 24 or 4. As such, all the nodes that could ever need to be rebalanced are on the path from the node we changed to the root. It follows that all the nodes that we have to rebalance, there are big O of log n of them. So we know that there are at most O of log n nodes that have to be rebalanced, and there are at most 2 tree rotations needed to rebalance each node that needs to be rebalanced. So that means that a cost function for the delete algorithm would look something like 2 times log n times whatever constant number of steps it takes to pull off a tree rotation. So it's O of log n. Deletion takes O of log n time for AVL trees. So now we're back to the case where things were annoying in binary trees. This was the hard case. Probably feels easy in retrospect, or at least less hard than deletions for other tree types. But this is when the node that we're trying to delete has 2 child nodes. we start off doing the exact same thing we would do before in a binary search tree. We find the node's successor and swap the node to be deleted with the successor. I won't go too in depth on how the successor works because I've already taught it, but to quickly go over it again, it's the node that would be right after the node we're deleting if you were to lay out all the nodes in order. So we swapped them, and now we delete it. We're going to move 19 upwards to replace the node we just deleted, and then go up the tree, ignoring this. Don't read that. Don't read it yet. We're going to go up the tree and check whether each node on the path from the node we just deleted to the root is still balanced. Okay, 19's children have equal height. That's good. Zero and 1 are close enough. They're only off by 1. So node 20 is balanced. The children of 17 have balancing factors that are off by at most 1, so that's fine. And so do the immediate children of 10. So, yeah.
When it comes to getting like the height and like finding out the balance, would the height number be like attached to the nodes, or would we have to like for every node get the calculation for the height?
Yeah. It's up to the programmer. There will probably be like application-specific considerations that would lead you to take one choice or another. But taking nothing else into account, I think I would recommend not storing the height, like calculating the height every time you need to use it. Because if you're storing values like that, then you can forget to update them and then run into glitches that way. But on the other hand, the thing I suggested will take more time than just storing the heights. So there really is no perfect solution to it. Do what makes sense for what you're programming. Anywho, 3 minus 2 equals 1, so we're all good. We found that this one's balanced, this one's balanced, this one's balanced, and this one's balanced. Everything on the height, on the path to, everything on the path from the node we just deleted to the root is balanced. So we can have the startling revelation that no balancing was required. Cool. Just like the old delete operation, finding the successor to a node requires O of log n time, because in the worst case, you'll end up traversing an entire branch of the tree, O of log n nodes. The swap operation requires O of 1 time. And so the revised delete operation requires O of log n time. I think this slide's missing something though. We just talked about the maximum number of swaps, maximum number of rebalancings that must take place. We found that on the path from the node we just deleted to the root, we would have to rebalance at most log n nodes. Each rebalancing would take constant time. So I think this slide isn't wrong. Doing the log n successor finding operation and then doing log n rebalancing operations, we'll still end up with log n time overall. So the slide's right. It's just missing details. I'd probably deduct like half a mark from it if I saw this, or if the markers saw this. They would deduct it. Okay, I think we're done with AVL trees. Finally. I don't like AVL trees. And since we already talked about heaps, we're done with these slides too, which means we get to move on to the course's very last topic. More heaps. So if you're hoping to stop drawing circles and lines, you're going to be disappointed because we're finally going to get to the very nice generalization of trees, graphs. This first lecture on graphs is just going to be talking about definitions, like overview of graph theory, and then we're going to start talking about how to make them and work with them on a computer with algorithms. So, if you've already been exposed to graph theory through courses like Math 1240, this might be a little boring. But if you haven't, if you think that a graph is something that looks like this, listen up. A graph is a construct consisting of two sets. One set V is, it contains nodes, or we call them vertices too, and another set E of edges, where each edge represents a relationship between two of the nodes in V. The empty graph is right here. It's all across the page, actually. You could have a graph with no nodes and no edges. You could also have a graph with one node and no edges. And finally, third example is a graph that you might actually see. This graph has 4 nodes and 6 edges. And I'm going to use this example to actually go over what a graph looks like mathematically, because this picture doesn't really look like a set V of nodes or vertices and a set E of edges where each blah, blah, blah. It's a bunch of circles and lines. So what this picture at the bottom of the slide is mathematically is 2 sets. V is the circles. And then E is the lines. How you represent the lines will actually differ from case to case. But for this kind of graph, a simple graph, we're going to note the edges as subsets of V, subsets that contain exactly 2 elements. So AB is an edge, BC is an edge, CD is an edge. You won't believe this, but DA is an edge. Then we also got to get the diagonal lines. I think we already got one of the diagonals because this graph is laid out weirdly. And BD, I think. Uh, no worries. In this case, the elements of E were all subsets of size 2, but then there are other representations we could use. I might be getting ahead of myself, but there are directed graphs where, like, in this modification I just made, B is connected to A, but A isn't connected to B. So we would use ordered pairs to represent edges instead, because for those order matters, but for sets, they don't. There are also hypergraphs. We're not going to talk about them in this course, but I think they're neat. It's a generalization of graphs where the subsets in E can have any size. So, like, I just added a hyperedge that connects A, B, and C. Don't worry though, we're only going to talk in this course about lines that connect two vertices, or nodes, or whatever. I'm probably going to mix up those terms a lot. And also, for completeness, I'm going to write out V and E for the other two graphs because it's really straightforward. This one has V with just one element and E with nothing in it. And this one has both sets empty. V and E still exist. They're still sets, but they're empty, like an empty box. Here's some more stuff that we're probably not talking about in this course. It's just some other ways you could represent graphs. A loop connects an edge to itself. I suppose you would represent this as a set with one element. And then sometimes you could have multiple edges connecting two nodes. And I have no idea how you'd represent those using sets. You would need to use some different object that has some different metadata that allows you to tell apart two instances of an edge connecting A and B. Because if I wrote this, every math professor in a 5-mile radius would get mad at me because sets can't have duplicates. Just occurred to me that multi-sets exist, though. So you'd probably represent this with a multi-set of sets of size 2. Whatever. Don't worry about this. I'm pretty sure you won't have to worry about this. They're definitely not going to be on the next assignment. So we're going to talk about things that aren't these, simple graphs. Yeah, more definitions. The degree of a number, or the degree of a node is the number of edges that are incident with this node. What does incident mean? It means that an edge connects that node to another. In terms of sets, we would say that an edge is incident with a node if that edge contains that node. So the graph we saw above has the degree of every node as 3. And then below that is a graph with vertex degrees 0, 1, and 2. Also, I think I talked about this earlier in the course, but I I should probably repeat it now that we're doing a dedicated lecture on graphs. Graphs are super useful for a lot of things. Any context in any field of study where you have things that are related to each other, which tends to be a lot of fields of study, you could use graphs. The metaphors that come up most often for graphs, just when I'm thinking about them, are navigation and social networks. So in navigation, the nodes would be like buildings, cities, what other things exist? Countries. And then edges would be navigation paths between them. Maybe the edges are bus routes, and then two locations just don't have bus routes between them because they're in different cities. I don't know. This will be more applicable when we get to weighted graphs, where edges can have numbers associated with them. And then those numbers can represent like how far away nodes are, or how much it costs to get from one point to another. And then the other thing, another nice way to think about graphs is social networks, where the vertices or the nodes are people, and then the lines are some sort of relationship, like either friends or coworkers or something. So in this below graph, in a transportation metaphor, maybe this is roads from city to city, where node B is an island, and there are no roads to an island. Unless you make a bridge, I guess, whatever. But then you could get from A to C. And if you want to go from A to D, you'll have to go through C. And then in social networks, I guess B has no friends, kind of sad. C is very popular though. If A wants to talk to D, they'll probably have to talk to C first. Oh no, my metaphors are breaking down. Does a city have a road to itself? Can you be friends with yourself? I don't know. In a strictly theoretical sense, when you have an edge that forms a loop, so it connects a node to itself, then that edge is incident with the node twice. So in this diagram, the degree of A is 2. If I added another node, then now the degree of A would be 3. It's got that edge, this endpoint of that edge, and that endpoint of that edge. You may notice that if you add up all the degrees of all the nodes in V, you'll get a pretty neat little formula. I think this is used a lot in proofs of properties of graphs. Every edge in G, the graph, is incident with exactly 2 nodes. So if you add up all the degrees, you'll count every edge exactly twice. And then you get that formula. One application of that formula I just thought of, say you're storing a graph in code and you want to know how many edges there are, but you're not storing the number of edges for whatever reason. Loop through all the vertices and then add up their degrees, add up, and then divide that result by 2, and you'll get the number of edges. More definitions. I don't like these. It's way too easy to confuse paths, trails, walks, and cycles. Um, I will probably never quiz you on these definitions. And if I do, I'll give you a lot of advance notice. Even so, it's good to know about them so that you can speak about them clearly. And much more importantly, you can listen to someone who knows a lot about graph theory and remove any room for misinterpretation when they talk about like a walk. You know exactly what they're talking about. So, a path through a graph is a sequence of distinct edges connecting one node to the next, such that each node on the path is visited exactly once. So, I'm just going to draw a graph to use as an example. So A, B, C, D is a path. A, B, C, D, A, like going on that path and returning to where you started, is not a path because A appears twice. And if you go, I don't know, A, C, B, C, D, A, that's super not a path. You just wandered around. But it is a trail. Trails, actually don't quote me on this. I don't remember exactly what line I drew through the graph. But in any case, a trail is a generalization of the path where you're allowed to repeat nodes, but you're not allowed to repeat edges. So A, C, B, A, D is a trail. Actually, I'm going to see if I could use a different color. Yeah, that's slightly less confusing. A, C, B, A, D is a trail. It's not a path because we went to A multiple times, but it's okay because we went on each edge exactly once. A walk is a further generalization of a trail where you can visit edges more than once. So, I don't know, you could just do whatever you want. Whatever the heck I just did is a walk. And with those three definitions, you're going to get them confused. I guarantee it. But you can still somewhat use your intuition to remember which is which. Like, a path goes from one place to the next. It's more straightforward. A trail is a bit more free-form, but you could still imagine some structure. And then a walk. At this point, you're just wandering around. You say you're going for a walk, you're probably not going from a specific starting point to a specific destination. You're probably going to visit the same place twice. Much more freeform. Anyway, finally, a cycle is basically a trail. It starts and ends on the same node, but contains no other duplicate nodes. So you could think of it as a slightly more restricted trail or a slightly less restricted path. It doesn't really matter to me. So the edges are all distinct, and all the nodes except the first and last are distinct. ACDBA is a cycle. A, C, D, B, C, A is not a cycle because we repeated vertex C, and we also repeated the edge C to A. The important terms that'll come up in this course are path and cycle. Here's some more examples. Probably should have just scrolled between these slides. A, B, C, E, F is a path from A to F. A, B, C, E, F. Every vertex is unique. Every edge is unique. B, C, E, B is a cycle on the vertices B, C, and E. Every node except the start and end are distinct, and all the edges are distinct. Is BCB a cycle? I don't know about you, but I see some indistinct edges. You go on the edge connecting B and C twice, so it's not a cycle. These definitions just keep on coming. We've got at least 3 more. At least. A graph is connected it's connected for all unique pairs of vertices. So more formally, x and y in V such that x is not equal to y. There's a path in G from x to y. The first graph on this slide is connected. Given any pair of vertices, let's say C and A, that's boring. There's obviously a path from those. A to D, you could do that. F to C, yep. You can get from any one graph to any one vertex to any other. And then the other one is disconnected. You could see the total lack of connections from A and B to the rest of the graph. Remember the transportation metaphor. These could be cities and the roads between them, where A and B are just on a different landmass from the rest of the area represented by the graph. A graph is complete or fully connected if for all unique pairs of vertices, there's an edge in E between x and y. The first graph here is complete. The second is incomplete. So on the first one, you could get any pair of vertices and just have a simple straight line between them. But in the second one, B and C are disconnected, and A and D are disconnected. Want to really drill these metaphors in. For transportation, these would be a bunch of cities that all have roads or highways connecting each other directly. And the other, you would have to go through some other city first. Reminds me of having to stop in Toronto before flying pretty much anywhere else. And then for social networks, the complete graph has everyone knowing each other. And then the incomplete graph, A and D and B and C maybe don't really like each other. Maybe they just haven't met yet. But everyone's at least a friend of a friend or knows each other indirectly. These guys you've seen before. I think this was a quiz question back in the day. A tree, in terms of graphs, is a connected acyclic graph. Oh yeah, neither of these are trees. I was going to draw one of these as a tree. I'm going to attempt to prove a point. So I'm going to choose B as the root. It's going to have a child A. It's going to have a child E and a child C. This is fine so far. It's a tree, but not a binary tree. E has children D and F. And this is fine, I think, but it's not because there's an edge between A and C. This breaks our parent-child metaphor. It makes it so there isn't a coherent notion of things like a path from the root to a leaf anymore. We can't reason about these like we did with trees before. This one is also not a tree because, well, yeah. In fact, the word for graphs like this is a forest because it's a bunch of trees. So in this sense, our parent-child metaphor breaks down, but in a different way. Instead of there being multiple ways to get from a root to a leaf, now there are nodes that are just completely inaccessible from each other. And there are multiple roots. It's messy. Thankfully, these two are both trees. This is cool. You might actually be able to draw this as a binary tree if you try hard enough. Probably not the case. Never mind. I don't think you can get around the fact that these two edges have degree 3. Oh wait, no, they could have a parent and 2 children. It's a mystery that will remain unsolved. Maybe I'll put it on a quiz. Anyway, the second graph is a tree. In fact, it's the kind of tree that we would call degenerate if we were talking about binary trees, because this one just has each node with one parent and one child. If we were hoping for logarithmic time searches, nope. Stop hoping for those. Yeah, we have another definition here. Next slide. The slide after that doesn't have a definition. I was looking ahead just a second ago and it was like, oh, sweet, I think we're done. We're not. I'm going to keep telling you guys what things are in graph theory till the end of time. Oh yeah, subgraphs. This is like the idea of subsets, but for graphs. It even uses subsets in the definition. A graph is a subset of another if its vertex set is a subset of the other graph's vertex set, and its edge set is a subset of the other graph's edge set. So with G and a subgraph of G as seen here, the vertex set, you can see it's a subset. Every vertex in the subgraph is also in the original graph. Likewise, every edge in the subgraph is also an edge in the original graph. If I added this edge, it would no longer be a subgraph because it has an edge that wasn't in the original. A spanning tree is a subgraph such that the graph contains all the nodes of the original, and it's a tree. I'm not sure how often any of these will come up ever again, but spanning trees are super useful as a way to make a graph more streamlined. This will make more sense once we get to weighted graphs, which we will in like 1 or 2 slides. I talked about this already. In the transportation metaphor, frequently travel from one location to another has some sort of cost, like takes more time to get from one place to another, you have to traverse a greater distance, you have to spend more money. This happens often enough that we have a tool to represent situations like these. A weighted graph, not sure if I like this definition. So formally, we say that it has a weight function that maps edges to real numbers. But I think that's a bit stuffy. The way we're going to be thinking about it in this course is just that each edge has a weight associated with it. That's it. You draw numbers next to the lines. This weight function thing is still useful because it gives a mathematically precise expression of exactly what we're doing. But I'm never going to make you talk about the weight function on an exam. So, given weights on edges, the weight of an entire graph is a sum of the weights of all the edges. And then we can also assign a weight to a path, which is, again, the sum of the weights of the edges in that path. In the transportation metaphor, the weight of the graph doesn't mean that much. Not sure why you'd be interested in the total distance of all roads in a city. But the weight of a path makes perfect sense. Say you wanted to travel from city A to city E, and you wanted to know how far away it is. This hypothetical edge would probably be faster, but it'll probably make you drive off-road the whole time. To get from A to E, you're going to have to go through B, like that. So the distance from A to E, not in terms of absolute physical distance, but distance you'd have to travel by whatever transportation device you're using, would be the distance from A to B plus the distance from B to E. It's nice. So let me just take the last minute to talk about the quiz. I don't know how far I expected to get through this lecture, but we haven't really covered anything data structure E. Something that's definitely going to be on the exam or the next quiz is how graphs are represented in computers, but we don't know about that yet. So I'm probably going to really want a definition or few. Like, is this graph a tree? Is this graph a subgraph? Is this graph connected? Stuff like that. And I'll probably throw in something about an AVL tree rotation. All right, that's it. I will post the assignment as soon as I can and see you on Friday.